Well, the electron cloud.
Huh?
Seems straightforward, maybe.
You'd think so, but these sources really zero in on the edges. Or maybe the lack of edges.
Right. Where does it stop? And the big takeaway from your material seems to be, it doesn't. Not really.
That's the core of it. The quantum view suggests that, probabilistically speaking, the electron's influence, its potential location, it technically stretches out forever. Infinitely.
Which sounds completely counterintuitive.
It does. So our job today, using your sources, is to unpack that. Why no sharp boundary? What does infinite extension actually mean for an atom? And crucially, why does this fuzziness matter so much?
Okay, let's unpack this. Maybe start with how we even got to this cloud idea. The old picture was simpler.
Much simpler. The Bohr model,
Yeah.
electrons like little planets.
Orbiting the nucleus. Very neat, very clockwork.
Very intuitive.
Yeah.
And useful for a time. But, as your sources point out, it just didn't hold up against experiments. Things didn't behave like tiny solar systems when scientists looked closer.
So enter quantum mechanics. And your material flags a few key milestones here.
Yeah.
First, de Broglie.
Louis de Broglie, yeah. His insight was that electrons aren't just particles. They have a wave-like nature, too. Wave-particle duality.
Which must mess with the idea of a neat orbit.
Absolutely. And then Heisenberg comes along with the uncertainty principle.
Right. You can't know exactly where an electron is and exactly where it's going, its position and momentum simultaneously.
Precisely. If it has this wave nature, pinpointing both properties with perfect accuracy is fundamentally impossible. So forget those fixed, predictable paths.
It just blows up the whole planetary model.
It really does. And that leads us to Schrödinger and his equation.
The famous one.
That's the one. Solving it gives you these things called wave functions, usually written as a k, pi I psi. And these wave functions, well, they describe the electron state. They replace orbits with orbitals.
Okay, so orbitals aren't paths. What are they then, according to these sources?
They're related to probability. The wave function itself doesn't directly tell you the electron is here.
Mm-hmm.
Instead, you look at the square of its magnitude, written as coulomb, and that gives you the probability density.
Probability density, meaning?
Meaning the likelihood, the chance, of finding the electron within a specific, tiny little volume of space near the nucleus. High probability density means a higher chance of finding it there if you looked.
Ah, okay, so the electron cloud graphic we often see, that's just visualizing this probability.
Exactly. It's a map. Denser areas on the map mean higher probability, sparser areas mean lower probability. It's crucial, as your sources stress, not to think of it as a literal physical fluff ball.
It's a likelihood map.
A likelihood map. We've shifted from the certainty of Bohr's orbits to the probability clouds of quantum mechanics.
A really fundamental shift in thinking. So if it's a probability map, why no edge? Why doesn't the probability just stop somewhere, hit zero?
It comes down to the math. The nature of those wave functions, the solutions from Schrödinger's equation.
Yeah.
They don't just sort of fall off a cliff at a certain distance. They fade out gradually.
How gradually?
Typically, the decay is exponential. Think of functions like e to the minus distance. As the distance r gets bigger, the function's value gets smaller and smaller, closer and closer to zero.
But mathematically, it never actually reaches zero, not at any finite distance.
Exactly. It gets incredibly, mind-bogglingly small, but never strictly zero.
Ah, like the ripple analogy in the sources. Drop a stone in water, the ripples spread, get fainter.
But theoretically, that disturbance, however tiny, extends across the whole pond.
Okay. And since the probability map comes from that wave function.
And inherits that same property, the probability density also decays exponentially. It gets smaller and smaller the further you go from the nucleus, but there's no finite distance where it suddenly becomes absolutely zero.
And that's why the sources say the cloud technically extends outwards infinitely, because the probability, however tiny, is never exactly zero.
That's the direct mathematical consequence, yes. For an idealized, isolated atom described by the Schrödinger equation.
Okay, here's where it gets really interesting, and frankly, a bit weird. Your sources mention this implies, what? A tiny, tiny chance of finding an electron from an atom in my finger, out past Mars, or even further.
In principle, according to that pure mathematical model, yes, a non-zero probability. vanishingly small, practically negligible for almost all purposes, but technically not zero.
Wow.
It really highlights how different quantum reality is from our everyday intuition about objects having definite boundaries.
But hold on, chemists, physicists, they do talk about the size of atoms, right? They
But
give values for atomic radii. How does that work if the cloud is technically infinite?
Right, they absolutely do. They use practical definitions, as your sources explain, because while the probability technically never hits zero, it drops off very, very quickly.
So most of the probability is packed close to the nucleus.
Overwhelmingly so. So a common approach is to define a boundary surface that encloses, say, 90% or maybe 95% of the total probability of finding the electron.
Ah, so it's like saying, okay, it could be further out, but the overwhelming likelihood is it's within this volume.
Precisely. It defines a region of significant probability. It's a practical way to talk about the orbital size.
And the sources mentioned other radio, too. Van der Waals, covalent.
Yeah, those are based more on experimental observations of how close atoms get to each other in different situations when they're just bumping past each other versus when they're actually chemically bonded. They reflect how atoms interact in reality.
So these practical sizes aren't denying the infinite tail. They're just focusing on the region where the electron is, most relevant.
Exactly. They define the atom's effective reach in chemical and physical interactions. You need these practical measures to do any real chemistry or material science.
Okay, that makes sense. We have the theoretical infinite bit and the practical measurable bit. So let's talk about the implications of this fuzzy probabilistic nature. Why is it so important?
Oh, it's fundamental to almost everything. Think about chemical bonding. How do atoms stick together to make molecules?
They share electrons, right? Or transfer them.
Yes, but how? It happens because their electron clouds, these fuzzy probability distributions, can actually overlap and interpenetrate. If atoms were hard little balls with sharp edges, they'd just bounce off each other.
So the fuzziness allows them to actually merge, in a sense?
In a probabilistic sense, yes. It allows for the sharing or shifting of electron density that constitutes a chemical bond. It's essential.
What else?
Intermolecular forces, the weaker attractions between separate molecules. Things like van der Waals forces, specifically London dispersion forces.
How does the fuzziness play in there?
Well, even in a neutral atom or molecule, the electron cloud isn't static. It's fluctuating. At any given instant, the electron density might be slightly uneven, creating a temporary, tiny dipole. A slight positive charge on one side, slight negative on the other.
Okay.
This fleeting dipole can then distort the electron cloud of a neighboring atom or molecule, inducing a dipole there too. And then these temporary induced dipoles attract each other weakly.
Ah, and that attraction depends on how diffuse and easily distorted those clouds are.
Exactly. The squishiness or polarizability of the electron cloud, its fuzzy nature, allows these forces to arise.
And reactivity, how atoms actually do chemistry.
That's all about the outermost electrons, the valence electrons, their orbitals, the shapes and energies, and how far their probability clouds extend dictate how an atom will interact. Will it lose an electron easily? Grab one, share. Is all determined by the properties of that outer fuzzy edge.
The sources also brought up quantum tunneling. That sounds exotic.
It is pretty mind-bending. It's the phenomenon where a particle, like an electron, can pass through an energy barrier, even if it doesn't classically have enough energy to go over it.
Like walking through a hill instead of climbing it.
Kind of, yeah. And it's possible because the electron's wave function, its probability cloud, doesn't just stop dead at the barrier. A little bit of that probability, that exponential tail we talked about.
It leaks into and through the barrier.
Precisely. So there's a tiny but non-zero probability of finding the electron on the other side, even though classically it shouldn't be able to get there.
Wow. And the sources say this isn't just theory, it happens in fusion, in enzymes.
Oh yes, it's crucial for understanding certain nuclear fusion reactions in stars. It plays a role in how some enzymes catalyze reactions in our bodies. It's a real measurable quantum effect enabled by that non-zero probability tail extending into forbidden regions.
So if we connect this all up, this fuzzy probabilistic electron cloud isn't just some abstract mathematical idea.
Not at all.
No.
It's a fundamental reason atoms can interact, form bonds, create materials with specific properties. It's the basis of chemistry and much of physics. That fuzziness is the reality at that scale.
Okay, so let's try to wrap this deep dive based on your sources. We started with the old, neat Bohr model, but experiments pushed us to quantum mechanics.
Right, which gave us wave functions, probability densities, and the idea of the electron cloud as a likelihood map.
And that map doesn't have sharp edges because the underlying math, the wave functions, decay exponentially. They fade out, never quite hitting zero.
Leading to that technically infinite extension, which is pretty strange but mathematically sound for the idealized model.
But in practice, we define atomic size using high probability boundaries or by looking at how atoms actually interact.
Making it usable for science.
Yeah.
And this whole fuzzy probabilistic picture is absolutely key. It explains bonding, forces between molecules, chemical reactivity.
And even weird stuff like quantum tunneling. It's fundamental.
Absolutely fundamental. And maybe here's a final thought, stemming directly from your sources. If every electron's probability cloud technically extends infinitely, what does that really mean for the concept of empty space? Is the space between atoms or even between you and the screen you're looking at ever truly quantum mechanically empty?
That is definitely something to ponder. Thank you for guiding us through these sources and unpacking such a fascinating concept. And thank you for joining us on this deep dive.